G'day. Hope you're enjoying this Saturday morning. I'm here today because I want to inspire you. I want to light a spark in you about global collaborative software development. Hi, I'm Simon. I'm from the Riverina Cancer Care Centre in Wagga Wagga. Back in April 2019, it seems like a lifetime ago, the first picture of a black hole was made. This was done to test Einstein's theory of general relativity. That black hole was 40 microarc seconds on our night sky in size. That's like trying to take a photo of a grain of sand on the Gold Coast while standing in Perth. They needed to build an Earth-sized telescope. We don't have Earth-sized telescopes, so they linked telescopes all around the world using software and atomic clocks. That network of telescopes recorded a huge amount of data, and all the code to process that data and return this image that you can see here was open source. This collaboration was built on open source software and built from scientists all around the world coming together, sharing the work they were doing, not hiding it behind their closed doors. I want to do that in medical physics. The seeds of it are already there. There are people around the world releasing software in medical physics, sharing knowledge, and sharing the software that helps that knowledge work. My goals for this talk, as I said, is to inspire you about what's possible when we write software together. I want to give you a lay of the land of the scientific Python ecosystem and the medical physics Python ecosystem. I recognize that many of you haven't programmed very much. You might have done a little bit in your masters, a little bit in your undergrad, probably MATLAB, maybe a little bit of Python, but very little. I want you to know what's possible. I want to give you an idea of what you can Google on that day when you have a problem to solve and you go, ha! There was something that I knew something that was made out there to do that I can use today. And that'll help you. So I hope that'll help you. I also then want to present a few of the tools that we're using at our clinic. And you may want to consider collaborating with us. Even if you don't have much software writing experience, I'm so keen to just bring you on board. You could help with trying to use the tools and then giving feedback on where you're struggling. You could help with trying to use the tools and improving the documentation that's around it. You could, you could be a gun-ho at all this Python coding stuff and make new tools that we can all use together. During this talk, I'm going to be active in the Zoom chat window. Magically, I'll be in two places at once because I'm actually recording this. Spoilers. And so I'll be actually available to answer you in the chat window. And I'll also copy a link to the slides and this video into the chat window as well. So, the scientific Python ecosystem. It's amazing. In the core of it, there's a few packages: NumPy, Matplotlib, SciPy, and Pandas, and a few others too. NumPy is like it's an array and matrix library. It's very similar to how MATLAB does its matrices and its arrays. So if you're familiar with how MATLAB deals with those sorts of things, NumPy is great for that. NumPy takes those arrays and does its computations very fast, so you can do things that are you can achieve speeds with that you wouldn't otherwise. Matplotlib is a brilliant tool to create production quality figures. It's very similar API to very similar interface, programming interface to MATLAB, so it's helpful if you're from there. SciPy is a great library that has a range of tools from things like interpolation to signal processing to optimization. There's a swathe of tools in their statistics. The SciPy covers a lot of what you would need when you're doing general scientific tasks. Pandas is a brilliant a brilliant table library. I personally love to use it to read and write CSV and Excel files in a programmatic way. Allows the data that I data I collect in Python to be able to be produced in a format that other medical physicists will readily understand. But that's just the tip of the iceberg for Pandas. It's got a lot of if you're keen on machine learning, Python has a range of libraries. Scikit-learn, TensorFlow, and PyTorch are some of the key ones, but there are more. But there's also other tools. For example, Streamlit. Streamlit is amazing. It allows you to build these GUIs, graphical user interfaces, and I'll show you one. One of the first tools that I present is using Streamlit. It builds these graphical user interfaces that you just couldn't do otherwise. Well, you could do otherwise, but it'd take a long time. It lets you make them very, very quickly, and they're very beautiful, and they're very easy for other people to understand, and the code that makes the user interface is easy to understand for everyone who has a little bit of programming experience. Shapely is a great tool, great geometry library. I personally used it to do some electron cutout factor modeling, but it's useful for those sorts of things. Scikit imaging is great for image processing, smoothing noise, and a lot of other things. Sorry, the light keeps going off in this room. There we go. Maybe we try and cut that. I'm not sure if I have to. Anyway, see how my video processing skills go. Jupyter is a brilliant library that lets you interactively code. It's a great way to learn to code, a great way to prototype and experiment. There's a library called Xarray, which allows you to keep handle of your dimensions. It's used a lot in climate science space. ITK is an image toolkit, and it's got some great Python bindings, Python interface. For example, if you know a little bit about deformable image registration, there's a range of deformable image registration implementations written in ITK, available in that library. Personally, and then when you're writing Python, there are a range of other tools that I would highly recommend. I'd highly recommend looking into VS Code if you're starting to get a bit more keen. And PyTest and Hypothesis are brilliant testing libraries that allow you to automate the testing of the accuracy or the correctness of your code. Lets you specify what the code should be doing and how it should be doing it, and do that automatically. And so in the future, when you make changes to your code, you can automatically run those tests and run all of the automated tests that you've ever written, and make it so that you can verify that you haven't broken something that previously worked. So, how did I begin learning Python? Well, my first port of call was this document called NumPy for MATLAB users. Here's the link here. It's got a brilliant table where on the left-hand column is what the MATLAB syntax would have been, and on NumPy, and then in the middle is what NumPy's syntax is. And you can see I found this really helpful because I had quite a bit of experience in MATLAB, and this allowed me to very quickly pick up Python and start running with it. I also very much used Jupyter, and you can have a play around with the Jupyter notebook here. Back then it was called IPython notebook, but this is really great to be able to write code and then see the results from your code, and quickly iterate and learn. So the medical physics Python ecosystem, it's growing, and one of the cornerstone libraries is PyDicom. In medical physics, we use DICOM for so many things, and we have a very robust library in Python to read and write DICOM files, and PyDicom is amazing. And we also have another library called PyNetDicom, which allows you to make a DICOM server and communicate with other DICOM servers. Brilliant for setting up a server that, for example, the planning system can send DICOM files to. You can do something with your Python and then send that back. So it's going into the more the medical, the radiation oncology side. We have PyLinac. PyLinac is a tool that was written by James Kearns during his PhD, and he continues to maintain it, and he's working at Varian now. And he's made a library that covers a range of tasks such as Winston Lutz, picket fence. Go have a look. There's a lot of tools there that you can use to utilize what he's got there. Back to DICOM. If you just want to quickly view a DICOM file, there's this one called DICompiler, which is a brilliant little tool just to look through the DICOM header and investigate things. Up next, actually, the creator of QA-Track Plus is talking, I believe, Randall Taylor. You can see here's a picture from his website of what QA-Track Plus looks like. Tools to be able to track your quality assurance over the each month that you do each month and each day and each year. You can set up your QA inside that and then trend it across all the Linux you have. And so yeah, but he'll tell you a lot more about that next session, so that's good. There's a sort of an upcoming one, PyQA server, pretty cool. It takes PyLinac and combines it with a DICOM server called Orthunk and tries to automate that process of you send DICOM files to this PyQA server and it automatically runs PyLinac processing on that. There's another one here, DVH Analytics, being used to trend plans as they're coming through and compare plans. And then there's the one that we've got, PyMedPhys. So, why did I make PyMedPhys? Well, personally, I wanted to use best practices to build, deploy, and share the software we were building. And I wanted to make a welcoming place for medical physicists to learn and share code together. Each of these libraries up here use a thing called Git and GitHub. And this can be complicated. And also, the learning curve to get on and start contributing to these, it can be daunting, and people sometimes don't want to jump in and have a go. I'm really keen on making it so that those who have some programming experience, who are writing some software in their clinic, can actually get involved in this medical physics Python ecosystem. Yeah, and so that's why I made PyMedPhys. So I want to give you a few examples of some of the tools we use. All these tools I'm going to show you are available within the PyMedPhys repository on that GitHub thing that I was telling you about. Documentation for PyMedPhys is up there. Not all of these tools are in that documentation. Some of them, although we use them clinically, they require more work before they are something that would be easy to use by someone external to here. Yeah, so the first of these three is going to be an MU density comparison utility. Well, MU density is just because I shied away from wanting to call it fluence. I wasn't a big fan of calling like a log file created fluence a fluence, because it's not really a fluence. So an MU density or a meter set map, or just a map of the MU coming out of or through the MLCs, but be able to compare that between a range of things, and I'll show you that more. We've got this a Winston Lutz Arc, so not just doing the Winston Lutz at 4 cardinal angles, but actually delivering a dynamic arc and essentially getting all 360 degrees and having the delivery be a lot quicker. And then I also want to show you a recent project that one of our master's students did from the University of Sydney, Matthew Cooper, some back-bag auto-segmentation. So, I'm just going to this is the MU density comparison tool that we use in our clinic here. We've hosted it across our 3 sites, and we utilize it. What this does is it connects to a range of data sources. It connects to Monaco, the direct back-end Monaco files, the original raw data, connects to DICOM files if you want to import them in, connects to Mosaic, the Mosaic database, connects to the live stream ICOM stream from the Electa Linux, and also the high-resolution TRF log files from the Electa Linux. So we've got 5 data sources of all that data is being collected for every treatment and every delivery. And this tool provides a way to readily compare that data. So it's a user interface to be able to compare that data. So let me pull it over here so you can see the link here. If you download these slides from this link, I'll copy the link into the chat window. I'll also, how about I copy this link into the chat window too, if I remember. If someone can copy it in for me, hey? At least me, let's hope. So copy that one in, and if we go here, here is, if you go to that link, this is what you'll see. And so this has what's called a simple mode and an advanced mode. So you can click here to run in advanced mode. It opens up a lot more tools. But let's just go through the advanced mode first, the simple mode first. So this red and blue is to mimic different clinics. So if you've got different sites, like so for example, we have 3 sites, so we'll have we'll have 3 options here. So let's pretend we're at the blue site, and the blue site here in this demo has a patient has only one patient in it. However, in the real version, there's going to be a lot of patients. So we write in that patient ID, and you can see here it's found this patient. The patient's called Test Physics. It's beautiful mother naming that child. Yeah, and there's only actually one plan in Monaco. If we, for example, go to the red clinic here and we go in 98989, you can see there was 2 plans found in Monaco, so you can see the selection there. But let's go back to this one. And so then you can select that one. And here it's comparing to the live data being collected from the data that's been stored from the live stream, the ICOM live stream. So you can pick a different timestamp of when that data was collected. And you can see here is sort of a quick sanity check. You can see the MUs agree between the Monaco plan and the ICOM stream. But then we actually want to do this MU density comparison. Don't on this server haven't set up for PDF reporting, but we can still see it. And you can see here my beautiful physics plan of a cube presenting some weird VMAT plan here. Nothing clinical, but anyway. And you can see here is the reference MU density that's pulled directly from the files coming out of Monaco, and here is the evaluation MU density that's come from the ICOM stream recorded from the LINAC. Cool. And so if we go run in advanced mode, you might not want to just compare the Monaco, you might want to be able to compare DICOM. So you can see here, you can upload some DICOM files and do things like that. We can also choose to search directly the Monaco file export location. So let's say we've exported this plan from this DICOM file from Monaco, and you can see that there. And you can see here's a DICOM file that's been exported from Monaco that's sitting in the DICOM export file. And we might want to be able to compare that not to you might be able to want to compare it to Mosaic, but we don't actually have access to Mosaic here. You could also compare it to a TRF file, and there's some TRF files here that you compare it to. But this allows you to, and you actually can compare between sites, so you could actually do have the Monaco being at one site and the delivery at another, and anyway, it allows you to cross-compare each of these 5 data streams to each other. We'll just turn that light back on. Alright. So, that's that tool there, the MU density comparison tool. Here is here's our Winston Lutz Arc tool. What this does is underneath the hood, it uses a basin hopping optimization method to find the field edge and the ball bearing, but it also double checks it with PyLinux. So PyLinux has now 3 versions of its Winston Lutz algorithm, each of them giving slightly different results, and some of them being more reliable than others. As of this talk, only those first 2 are I'm actually checking at those. I'll be bringing in PyLinux 3rd method shortly. So the idea is that each of these methods are all being compared to each other, and if any of them disagree, it'll flag that. And then importantly here, you get this visual check. So what it does is you can see this field, like this line going around here. This is where it takes this line here and plots the field edge of this side and the field edge of this side, and flips them. And essentially, if it's appropriately found the field edge, you would expect that these penumbras would overlap. And you can see the same happening on this side and the same happening to the ball bearing. So it allows to give you like a visual interface of, has this Winston Lutz tool done something weird? But then it actually takes the images. We've set it up so that we're actually pulling the data from the iView database when you run a movie and you deliver an arc, a Winston Lutz arc that goes through all 360 degrees dynamically. And you can actually get a plot like this from minus 180 degrees through to plus 180 degrees with the field center minus ball bearing deviations plotted both in the panel x-axis and the panel y-axis. You can see that there like that. Now this is actually we currently use this as part of our monthly, and here we have a currently non-clinical beam, our 10 MV on one of our machines, and it's got this interesting effect where for different dose rates, mind you, and only some gantry angles, it intermittently jumps, the position jumps. So you can see here we've got about a mil jump happening in this 10 MV beam, only for some dose rates. So this Winston Lutz Arc is giving a dynamic beam that's much more like what is happening during true VMAT or true SRS, true SBRT. And it's using, and it takes just 1 minute to actually do the delivery for all 360 degrees. So you can quickly take different dose rates and get a huge amount of data. And as you can see, when you do that, you find things. Things that, in this case, send a beam to be non-clinical, which we're struggling to work out how to solve this. This beam has been unusable for a little while now. Cool. So that's the Winston Lutz. I have another one. Recently we had a master's student, Matthew Cooper, and I'm going to let him take over from here for a moment. He's got presented a little video of what he achieved during his master's project that's on PyMedPhys.
This video highlights a 2D UNet model trained to infer vacuum bag contours from canine CT scans for radiotherapy. The imaging series is exported from the treatment planning system to a DICOM server running remotely. From here, the DICOM service provider produces inference via TensorFlow. Once completed, a DICOM service user forwards the images and RT structure set back to the treatment planning system where it can be imported. This software handles multiple exports by storing jobs in an inference queue. Clinical acceptance testing has shown a 30-minute improvement in contouring time per patient. This model was deployed under a prototype warning and is currently being utilized on all new patients to reduce contouring times.
Cool. So as a first step, Matt implemented vac bag contouring. He's also utilized his same neural network architecture for prostate, bladder, and rectum, with a goal to have an automated contour checking tool. So this one was used to automate vac bag contouring, but in our patients here, we'd like to make it so that automatically every contour is able to be sort of doubled up, done again by a machine, and just to see, have it highlight if there's any deviations and flag them. In the recent TG275, they found that when they did a TG100 approach, failure mode approach, they found that the number 1 and number 7 largest issue, or highest risk issue, highest scoring issue, was both to do with contouring. And an automated contouring tool, QA tool, that was validating independently contours that are being created would be very valuable. And this is these here are listing human mistakes, but we're bringing out the vendors are bringing out auto contouring, and it would be really helpful to have an independent auto contouring tool, at least providing another layer of cheese in those cases. So what next? Do you want to collaborate with us? I'd be keen. Please reach out to me via email. me@simonbiggs.net is an email address there, or reach out on the PyMedPhys mailing list. You can see there's the link there. I've got a few acknowledgements. If I was to truly list all the people who made the software that we write possible, it wouldn't be able to fill the books. I wouldn't be able to fit it in the books in this room. But some of the key people: Darcy Mason for writing PyDicom, Patrick, and I don't know Skara Melian's real name, but Patrick, they've made PyNet Dicom. Matt Cooper for his great work on his master's project, James Kearns for PyLinux, my colleagues Jacob, Matt, Amy, and Nick for providing feedback when I write this software and helping make it be the best that it can be, and to all the PyMedPhys contributors for being the community that we're trying to build. You can download these slides and this video from these two links: simonbiggs.net/ACPSEM-Summer-School-2020-slides or -video. Thank you. Feel free to ask me some questions. Cheers.